Hey, welcome back. So this is 9.5. We're going to be working with alternating series. So up to this point, I believe most of the terms of our series were positive numbers, and even the limit comparison test, the direct comparison test especially, you need to have those positive terms, right, for the whole proof thingamajig to pan out. And another thing that comes to mind, you're always working between kind of trying to get an intuitive grasp of the overall picture, and then there's all this underlying proofy stuff. Just be careful with any intuition in math or science. Oftentimes your intuition is incorrect. I mean, that's why we have math and science, is to avoid such issues. So the proof is where it's at. Trying to make sense of it on the surface level, you'll kind of produce these kind of childish-like interpretations of the universe to get you through. But ultimately there's deep, profound facts which hold everything together, which you may or may not have incorporated into your hard coding. It's some of these proofs are just a bit too much. Anyways, let's dive right in. So we're dealing with alternating series. So the thing we have in this section is going to be called the alternating series test. So first off, there's two different forms. And for these forms, we often kind of separate off the alternating part. So there'll be this -1 flip-flopping back and forth, and then there'll be this a sub n expression. Okay. So before, we've kind of been using a sub n to describe the entire expression for the terms of the series. Now we're separating off and saying, okay, there's two parts of the series. There's this -1 that's flopping back and forth, and there's the rest of the expression. Anyway, so you plug in 1, you get negative a sub 1. Then you plug in 2, -1 squared is positive now, so you get a sub 2 minus a sub 3 plus dot, dot, dot. Okay. Of course, you can have negatives on the other terms, but generally we're going to be doing n plus 1 or n. So don't do n minus 1. You kind of get the same thing. There are clever ways to get negative, negative, positive, positive. We don't get too carried away with it in this book. But this one will be positive first, and then negative second, and then etc. Okie dokie. So what is the alternating series test? Well, it's pretty easy to apply. So you'll say the a sub n portion is going to be positive, or non-negative, I should say. So non-negative means it's not like -5. It includes 0. So I should say positive. Okay, I think you have to say positive. Okay, so let a sub n be positive, so it can't equal 0. And then the alternating series of one of the above forms will converge when the following two criteria are met. So first, I'm going to require that the limit of this positive portion, the a sub n portion, is going to go to 0. And that's kind of very similar to the nth term test for divergence. If you remember, that was one of our tests. I should have put it in 9.1 and ended up putting it in 9.2. It said if you have a series like 1 over n squared, or maybe something better like tan inverse was the good example, and you take the limit of tan inverse and it's not equal to 0, which it isn't, right? It's equal to pi over 2, then the series diverges. Okay, so it's kind of like you just begin by doing an nth term test, but you're only doing it on the a sub n portion. And then you need to also have this other condition, and it has to do with the proof again. You need this proof to work, so we need these conditions to hold. And on the surface level, it may not make a lot of sense, but in the proofiness of it, it pans out. So the second criteria is you need that the terms of the series are non-increasing, right? So a sub n plus 1, the next term is less than or equal to a sub n, In other words, if we didn't have the equal sign, it would just mean that the terms are decreasing, but that's the same as non-increasing because it could all stay the same for portions. But we want this to hold for all n eventually. Not to overwhelm you, but in this step, you're going to be using the monotonicity test that I established in the monotonic convergence theorem. Basically, you'll show that a sub n plus 1 over a sub n is less than or equal to 1. Or you'll show that a sub n plus 1 minus a sub n is less than or equal to 0. Or you'll convert it into a function and show that its derivative is less than or equal to 0. Okay. The book does it kind of weirdly. I don't know what the heck they're doing. Like I said, they just put out the same book every year and charge everybody a red penny for it. But is that what they say? Is that the turn of phrase? Or a red penny? I don't know. So, anyways, I want to look at an example. Let's look at an example first, and then we'll circle back around and do the proof. So, what do we have? Number uno. The sum of -1 to the n plus 1 all over n plus 9. Okay. If you're looking at this, you may say, well, that maybe that's like a harmonic series, and maybe that diverges. But let's take a look closer, right? So first we take the limit. And again, note, we do not, in our analysis, include the alternating part. We separate off the a sub n portion and do our work on that. So I'm going to be looking at the limit not of -1 to the n plus 1 over n plus 9, but rather just the limit of 1 over n plus 9. And of course, that's an L over infinity form, which will go to 0. Secondly, then, I'm going to do this comparison, this monotonicity test, right? So I like to use the first one, this one right here. 9 times out of 10, it works. So I need a sub n plus 1. That will be 1 all over n plus 1 plus 9, which is n plus 10, divided by 1 a sub n, which is 1 over just what it is, right? Multiplying by reciprocals, I'll get n plus 9 all over n plus 10. And that will be definitely less than 1 for all n greater than or equal to 1, right? So we have these two holding, thus by the AST, alternating series test, the series converges. Okay, so why? Why does this work that way? Is it, well, it's kind of, the nth term test plus the fact that the terms are decreasing kind of implies, but I don't know. Does that really work? I don't know. So let's look at the proof of this thing. And see what we got. So we're going to consider just one version. We could do the other proof for the other version, but let's just focus on this guy. The other proof would be similar. If you want to test yourself, go and try it. But consider this series such that we have the first term positive, the second term negative. So note the even summation. These I don't know what to call it, the S sub 2n. What is S sub 2n? So that's the sum of the first 2n terms, okay? All right, so I have a sub 1 minus a sub 2 plus a sub 3 minus a sub 4 plus plus a sub 2n minus 1 minus a sub 2n. Okay. Note, if I went one more term, what's going to happen is this thing going to be increasing or decreasing? So S sub 2n, and I don't go that to 1, I go 2 ahead. Okay, so this is the sequence of partial sums of the even terms. Okay, so this a sub 1 minus a sub 2 plus a sub 3 minus a sub 4 plus blah, blah, blah. So this is S sub 2n, and then I add in one more term. So a sub 2n minus 1 minus a sub 2n, a sub 2n minus 1 minus a sub 2n plus a sub 2n plus 1 minus a sub 2n plus 2. Okay, so what is this thing that we're adding in? Is it positive? Well, yeah, it is positive, and it's part of it well, not part of it, but because the a sub whatever terms are decreasing. So, a sub 2n plus 1 is going to be greater than or equal to a sub 2n plus 2. So that implies this a sub 2n plus 1 minus a sub 2n plus 2 is greater than or equal to 0. In other words, the sequence of partial sums is increasing or non-decreasing, if you'd rather. So we notice the sequence of partial sums is increasing. Of course, we like to say non-decreasing. We also note, so what else? We note it's bounded above, believe it or not. Why? You could rewrite these things as kind of the a sub 1, and then you're subtracting a bunch of stuff off of it. Okay, so we also note this s sub 2n thing. If you were to rewrite it in a more suggestive way, so let's rewrite it as a sub 1 minus a sub 2 minus a sub 3 minus a sub 4 minus a sub 5 minus blah, 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 whatever that is. I think it's clear that so it thus becomes clear that s sub 2n is less than or equal to a sub 1, because all you're doing is taking a sub 1 and subtracting away a bunch of junk to get to to your next term in your sequence of partial sums. So what? Well, that tells us that we have s sub 2n decreasing and bounded above, and then that's the monotonic convergence theorem again. And so this sequence of partial sums, the even partial sums, is convergent. Okay, hence the sequence, the even sequence of partial sums, is convergent by the monotonic convergence theorem. From section 9.1, right? Okay, well, that doesn't quite say that s sub n is convergent, right? We note, okay, so at the side, and it's a lot of notation and junk, but what is this s sub n thing? S sub n is equal to the summation -1 to the n plus 1 a sub n from, well, I guess we got to change the notation. K equals 1 to n, so let's make these k's. And we've not really shown that the limit of s sub n equals something, right? We've shown that the limit of s sub 2n is equal to something. So somehow we have to get to this to this box right here. And the trick is going to be to show that the limit of s sub 2n is equal to the limit of s sub 2n minus 1. And basically, if the even terms and the odd terms of a sequence are going to the same place, you can intuitively think, well, any term is either even or odd, so that kind of encompasses the whole picture. It's like it forces the limit of the s sub n to just equal whatever these two equaled, right? So it's a factoid of life. You could go back to the strict definition and prove it. If the limit of the even terms and the limit of the odd terms are the same, then the limit of the other guy is equal to that limit. We'll just take that on faith for now, because this is going to be a long video. But how do I get the limit of s sub 2n minus 1? So what do? We next then consider that limit. First, just what is s sub 2n minus 1? Well, s sub 2n minus 1 is basically s sub 2n minus an a sub n, right? Or maybe plus a sub n, right? It has one term. is it minus or is it plus? I think we have to minus it away, right? It has one term less, so yeah, minus this a sub n. And then let's take the limit of it. We know both the limits of these guys. Remember, in the inequality, the conditions that we start out with, step 1 and step 2. Step 1 says that the limit of a sub n is equal to 0. Okay, so this limit right here, because of what we are trying to prove, that thing is going to be equal to 0, and thus this limit of s sub 2n minus 1 is just going to equal whatever the heck the limit of s sub 2n is, and thus we have what we need. Thus the limit of s sub 2n minus 1 equals the limit of s sub 2n, which equals L, and you could go back to the strict definition and prove this implies the limit of s sub n is equal to L, and that tells us basically that the sum, the series is equal to something. Okay, it adds up to something, and therefore it's convergent. It's useful. Okay. Okay, so there it is, more or less, in all of its glory. Let's actually, I think the application is much easier. It's just you have to be willing to stomach the fact that on the surface, you know, as you go through and you're doing your procedures, there's not a huge correlation to the proofs, and you're just kind of like memorizing, okay, I have to do this, I have to do this, right? And there's no rhyme or reason unless you want to dive into the deep end. Okay, but anyways, let's take a look at number 6. So I have the sum from n equals 1 to infinity of the sine of 2n minus 1 times pi all over 2. So, oh my gosh, what the heck is this thing? It doesn't have a negative 1 in it. Well, no, don't freak out. Just write it out. So I got sine of pi over 2 when I plug in n equals 1. 2 times 1 minus 1 is 1, so you get pi over 2. Plus sine of n is 2, so I get 4 minus 1 is 3, pi over 2, etc. Right? Sine of 5 pi over 2. And then what the heck are those things? Well, sine of pi over 2 is 1. Sine of 3 pi over 2 is negative 1. And then so on and so forth. A lot of people think, well, this must just equal 0, right? Well, no, it's not going to work that way. Let's go ahead and look at it, right? So this series, let's maybe rewrite it first off, is just negative 1 to the n plus 1 starting from n equals 1 to infinity. It's equivalent. Right. All right. So let's do the test. So the limit of a sub n, and it's not clear what a sub n is. If it's not, well, it's right here. It's just 1, right? So the limit of 1 as n goes to infinity is equal to 1, which is not equal to 0. And this guy is going to end up being divergent, but not necessarily because of this fact. You actually have to go to the nth term test and say the limit of negative 1 to the n is, the odd term's going to go to 1, the even terms will go to, if it's n plus 1, the odd terms go to 1, the even terms go to negative 1, and therefore the limit will not exist, and therefore it's not equal to 0, and then by the nth term test, it's divergent. Okay, so it's always going to have that kind of, that kind of, if the first step doesn't work, you're going to automatically be able to conclude, because it's always going to end up with these two kind of accumulation points. It'll flop back and forth around 0. Okay, so I'm going to say if that first step does not pan out for you, so if the limit of a sub n does not equal 0, I'll allow you to automatically conclude that the series diverges. But technically, again, it's not from just doing the limit of the term of the a sub n portion. It's actually the nth term test that you have to do, but I think we're okay with making that leap of faith. Okay, so that guy's divergent. Let's look at number 5. So that problem is a bit non-typical. Number 6 is a bit of a curveball, so that's why I wanted to do it, so you're not seeing in your homework having a a mathematical meltdown on me. This one is more of the flavor that I would put on a test or something. So I'm looking at the limit. Again, you just look at a sub n. You don't include the -1. And then, of course, this is L over infinity, so that'll be 0. So we're good there. And then I'm going to do a ratio test again. So 1 all over n plus 1, the 7th root of, so I'll just write 1/7, divided by 1 all over n to the 1/7. Do reciprocals. And of course, that the denominator exceeds the numerator, so that'll be less than 1. Therefore, it is non-increasing, and so the conclusion, convergent. Okay, so they're pretty simple once you get the hang of it, yeah. Okay. One thing we've not had to deal with for a little bit is actually finding what these series add up to. Okay, it's going to turn out that if a series is convergent, you're going to be able to approximate it just by looking at the first 10 terms of it. Usually that'll be good enough, unless it's a really slow converging type deal. So our first taste of doing this estimation of convergent series is the alternating series estimation theorem. Okay, so section 2, alternating series. I forget what they call it. Let me look at my notes. Series remainder theorem. Oh. I used to always call it the alternating series estimation theorem. I don't know why they're calling it this remainder theorem. Okay, but it used to be theorem 9.15, and what it says, first off, you need to have a convergent series for this thing to work, and it has to be alternating. Okay, you can't do this with anything else. But if it is alternating and it's convergent, so if you are given an alternating convergent series, then the difference between the distance between the actual sum, which I'll call S, and the nth partial sum, which I'll call S sub n, is going to be less than or equal to kind of the next term in the series, a sub n plus 1. Okay. They don't really prove it in the book. I'll kind of give you an intuitive reasoning as to why this works. If you think in terms of this guy being a series, so you have the series of -1 to the n plus 1 times a sub n from n equals 1 to infinity. So that's going to be a sub 1 and your plus. So you start out at a sub 1, wherever the heck that is. Maybe it's right here. And that's equal to s sub 1, your first partial sum, right? Okay, so a sub 1 plus, or rather it should be minus then. A sub 2. So what's going to happen is you're going to move over by a sub 2 to your next partial sum, which will be s sub 2. And then you're going to add in a sub 3. And because of the terms being non-increasing or decreasing, it's always not going to go as far over to the other side, right? So it's bounded above by a sub 1, and then these sums are kind of within 2 consecutive partial sums. The landing place is in there. So a sub 3, you're going to go back to the right, and then that'll be s sub 3. And then a sub 4, you're going to go back to over here, and then you're going to be right here, and so on and so forth. And maybe you get all the way out to s sub n. But the next, movement is going to be a sub n plus 1. And then this will be s sub n plus 1. And I think intuitively, and it's a little scary to use your intuition in math, but intuitively we could say that we know the sum, the actual value of the sum, is in there somewhere. Okay, so what's happening is that basically the distance between s and s sub n in other words, the distance from this S over to that S sub n right there, is less than the A sub n plus 1 that you use to move over to S sub n plus 1. So A sub n plus 1, again, is this movement, right? And that's the idea, okay? So to go from S sub n to S sub n plus 1, you move by A sub n plus 1, and you know then the distance between S sub n and S, which is right here in the middle, this distance is going to be less than this distance. Okay? So that's the intuition, not really a rigorous proof by any means, but hopefully that gives you some way to kind of latch on to the idea. Okay, so there's going to be two types of problems. One problem is basically how good is your estimation? And then how many terms do you need in order to get some estimation? So in one problem, they give you the n. And the other problem, you have to find n. So here I'm saying, how many terms do you need in order to minimize the error? Okay, so let's look at the first one. And in that case, the n value is given. We'll presume that the series is convergent, but you should be checking on your own to make sure that you're not being hornswoggled. Is that a real word? I don't know. I'm getting so old, I'm forgetting the words I knew when I was younger. Hornswoggled. Approximate this sum with the first 6 terms, and then give an estimation for your sum. And for a lot of these series, you don't really need that many terms to get an idea of what it will equal. Right? So anyways, first you want to get your hands on S sub 6. So I would use some sort of calculator, but we can write it out. You want to be a little sensitive to if you're starting at 0, if you're starting at 1, but ultimately you're just counting out 1. So right now I have 3 terms, 4 terms, 5 terms, 6 terms. Okay? And I went to my calculator and got an exact answer, so I have to mess around with approximations. Then I know from the theorem that S minus S sub 6 is going to be less than or equal to A sub 6 plus 1, which is A sub 7. And then A sub 7 is just, this, you're plugging 7 into that portion of the series. So it's 7 all over 2 to the 7th. Okay. Then I can create a sort of boundary around the actual sum by opening up this inequality. So this will be less than or equal to 7 all over 2 to the 7th, but greater than or equal to the negative of that. And then you could solve for S by adding S to the 6 to all 3 sides. And then you could get a computer approximation, probably for WebAssign. Okay. So I found that the sum is somewhere in between 0.1328 and 0.2422. Okay, so that's the first type of problem. The second type of problem, you're trying to figure out how many terms you need to make an error less than some bound. Okay, so approximate sum, so your error is less than 0.001. Okay, so the series in this case is -1 to the n plus 1 all over n squared, and we're starting at 1 and going to infinity. We know that S minus S sub n, and we don't know n is unknown, is less than or equal to a sub n plus 1. And in this case, a sub n plus 1 is 1 all over n plus 1 squared. And we want that thing to be less than 0.001. Okay, so what you do is work with this inequality. You could do trial and error if you want to. Sometimes you could solve the inequality directly. I think you could solve this one. So you get 1 all over, divide both sides by 0.001, and multiply both sides by n plus 1 squared. Take square root on both sides. 1 over 0.001 is the same as 1,000. Tens, hundreds, 1,000s. 1 over 1,000. Square root both sides. So we need n to be greater than whatever heck this number is. And that thing, if you go to your calculator, it's about 30.62. So that implies I need n equals 31. Okay? So for your quiz today, I want you to figure out that sum. So your video quiz, you're figuring out the summation from n equals 1 to 31 of whatever the heck it was, negative 1 all over n squared. Okay, let me pause the video so I can mark that down on my notes. Okay, whoops, I lost the exponent apparently. So this would be n plus 1. Please don't do it by hand. Go and use a calculator to get that number. 3 decimals, please. And that should be really, really close to the actual sum, right? It should be less than 0.001 off. Okay, so that's awesome. You'll use that later when we're doing integrals and trying to do approximations of certain integrals. The last topic here, I generally don't put on the test. It's the absolute convergence and conditional convergence issue. It is in the homework though, so I want to include it in my notes as well. So absolute convergence. Conditional convergence. There's other types of convergence. Please don't go flying out on the dark web and start bringing in things like uniform convergence to me. You'll learn those if you kept taking math and you took like a real analysis class or advanced calc. These are a little different, and they just basically will say how good is the convergence and with regards to ordering the terms. So if something is absolute convergence, you can kind of fiddle around with the summation. It won't really make too much of a difference. The conditional convergence is a little more sensitive. Okay. So anyways, there's a flow chart you need to follow. So basically you start by just looking at the absolute value of the terms of the series of the absolute value of the terms of the series and ask, is that convergent? If it is, then you're pretty much done. You have absolute convergence, which is equivalent, is also going to imply that it's convergent. Okay, so if yes, then the series is absolutely convergent. We'll say AC. Okay, and of course that also implies the series converges. But it kind of has a super convergence quality of absolute. If not, then we have to do additional testing. Okay? So you go back to the original series and work with that. And if that thing is convergent, it's conditionally convergent. I'll just write CC. Otherwise, it's divergent. Okay. So this test, this determination process is a little bit lengthy. I mean, worst case scenario, you'll have to go through basically 2 tests to make your conclusion. And okay, so let's go ahead and take a look. So look at number 12. I have this series -1 to the n all over n factorial. So first I consider the series of the absolute value of those terms. And this series, how do I take the absolute value? Well, it's going to just clear out all the negatives. So every term in your sum will be positive. In other words, you're just looking at 1 over n factorial. Okay, so is this series convergent? And I think it is. We do a direct comparison, right? So note by direct comparison, first off, 1 all over n factorial is going to be less than 1 over 2 to the n. The series of 1 over 2 to the n is geometric. R value is 1/2, so the absolute value of R is less than 1, so therefore it's convergent. And so our conclusion in that case, convergent. Both series are convergent. So that tells us that the series is absolutely convergent. Okay. I think if I ever did a proof of any of that, probably not. Let's look at number 13. So we have the series n equals 1 to infinity of -1 to the n plus 1 all over n plus 5. Okay, so again, first you consider the series of the absolute value of the terms. Okay. So the absolute value will just make all the terms positive, so you just be looking at 1 over n plus 1. What the heck is that thing? That's basically just a shortened version of the harmonic series. Okay, so this is divergent. Right, so if you were to expand that thing from n equals 1 to infinity, you're going to get 1 over 2 plus 1 over 3 plus dot dot dot, which will equal the sum from n equals 1 to infinity of 1 over n minus 1. Right, so you're just subtracting away that first term. And I had this theorem that said basically if you have the series from n equals 1 to infinity of a sub n behaving one way, the series where you either chop off or add a couple terms is going to have the same behavior. And so that's kind of what I'm getting at in that statement. Secondly, then, so where are we in the flowchart? In the flowchart, we've seen that the series of the absolute values of the terms is harmonic, so it's not convergent. So I go and look at the original series. Okay, so now I consider the alternating series. Okay, so our alternating series test, first we take the limit of the a sub n portion. That, of course, is L over infinity type, so that'll be 0. And then we do this ratio test, 1 over, I got to add another one in, so n plus 1 is n plus 2, all over n a sub n. So that'll be n plus 1 over n plus 2. That's, of course, less than 1, so it is non-increasing. And so our conclusion there is convergence. Okay. So above in the flowchart, we looked at the absolute value portion, the series of the absolute value. That is not convergent. But then we looked at the original series and found it was convergent. So overall, it's conditionally convergent. Okay. So hence, conditionally convergent. Let's look at one more, and there may be a homework problem I need to look at. So let's look at number 14. So this is the worst case scenario. This will end up being divergent, -1 to the n plus 1 times n all over 5n plus 3. Sorry about my handwriting. So first you take a look at the absolute value, the series. And again, all that will do is get rid of the n plus 1 object. So you're going to end up with a series of n all over 5n plus 3. Okay. We could do nth term test, the easiest test in the universe. So note, let your reader know what you're doing. Note the nth term test. And we take a look at the limit of n all over 5n plus 3. Circle out the high degree portion, so that limit will be 1/5. That's of course not equal to 0. That implies it's divergent. Okay, so then we go to the original series, and it's alternating. And the alternating series test, again, kind of starts with the nth term test, sort of. And of course, that thing will not equal 0. That will just equal 1/5 again. So again, we will say it's divergent. Okay. So hence, this series is divergent. Okay. Really quick then, because I know I'm going to get a ton of questions on this problem. I just want to look at WebAssign. I think it's in this section. I'll pause the video. I won't waste your time doing this. Okay, it's this number, well, maybe number 17 is hard, but you see the answer there if you're wondering. But number 18 is usually the one that people yell at me about. So find all x values such as a series converges absolutely and converges conditionally. If the answer is an interval, enter your... So what you're going to end up doing is kind of chopping up the number line into pieces and approaching it that way. And it won't be the best proof in the universe, but it's gonna get the job done. So this is actually problem 18 in WebAssign. You have the series x to the n all over n, and you're looking for where is it absolutely convergent, and then where is it conditionally convergent, and I think then where is it so absolutely, well, just absolutely and then conditionally. Okay. So again, what you're going to do is kind of split it so that you can attack the problem in interval via the intervals. So x less than -1, first off. So you could just look at an example. It's kind of like doing a test value on the number line. So pretty much everything will work the same. And that's kind of the iffy part of this process. It's not technically a good proof, but it'll get the job done. And that's all you need to do in this WebAssign stuff is get the job done. So first off, -2 to the n, I don't know why this gives people problems, but that's the same as -1 times 2 to the n, which is the same as -1 to the n times 2 to the n. So what you have is an alternating type series in this interval. And then you can just do the first part of the alternating series test is kind of the nth term test, where you're taking a limit of this thing. And it's infinity over infinity form, so you could do L'Hopital's, and of course that would be 2 to the n ln2, and you take its derivative over 1, and then that'll go to infinity. So it's going to be divergent when x is less than -1. Okay, so that part of the number line is kind of good. And then what happens exactly when x is equal to -1? Maybe that's different, right? So you get -1 to the n all over n. And that's alternating, so we do alternating series tests. So you take the limit of 1 over n, that equals 0. Well, first off, we should, keeping with the flow chart, first off, look at the series of the absolute value of the terms, right? So this, what is that? That's just the series of 1 over n, which we all know is the divergent harmonic. But that does not say it's not conditionally convergent, right? So secondly, then we take a look at the original series and, first take the limit of the a sub n portion. That's L over infinity form. That will be 0. And then look at the ratio of consecutive terms, reciprocate it, That's definitely less than 1. So yeah, this part is convergent, and thus overall it's conditionally convergent. Okay. So from the flow chart, when we get x is -1, that guy is going to be conditionally convergent. Okay, then I'm going to look in between -1 and 0. Okay, so at 0, it's going to be convergent. It'll just be the sum of 0. 0 plus 0 is 0. And you get the sequence of partial sums that just equals 0. And then the limit of the sequence of partial sums will just be 0. So I'll consider x values in between -1 and 0. So I'll have things like -1/2 to the n times 1 all over n. And of course, I'm taking this original as my form, right? So I'm putting -1/2 in for x, and then analyzing it. Okay. So what is this thing? You could break off the -1 to the n, and then you'll have 2 to the n times n. Considering the absolute value of this expression, you know, which is maybe what. No. Okay. So I got to see if it's conditional or if it's absolute. So I take the absolute value of the given expression. That will just be the sum of 1 over 2 to the n times n. And I mean, this guy is going to be, it looks like it's absolutely convergent, right? You can compare it, do your direct comparison. And that's a geometric on top. Hence, it's absolutely convergent. All right. The series, then when x is equal to 0, like I was saying, you'll have a sequence of partial sums which are all just zeros. And then if you take the limit of that, to get the actual value of the sum, it's equal to 0. Okay, so that guy is absolutely convergent. In that case, so we have this case, and then we want to look at values of x in between 0 and 1. So we know when x gets to 1, it's going to be divergent. So there's kind of when x is 1, it's the harmonic series, right? So x greater than 0 but less than 1. So you're looking at series like, well, that's basically just kind of the series we were looking at when we took the absolute value, right? So it'd be like 1/2 to the n times 1 over n, which of course is just a series of 1 over 2 to the n times n, which we just proved was convergent. So it's absolutely convergent here as well. And then where x is greater than or equal to 1, we have series like 3 to the n all over n. And those guys are always going to have the behavior of the harmonic. So you could do a direct comparison again and just compare it to the terms of the harmonic series. So this would definitely be greater than that. And then because it's above a divergent series, it'll be divergent. And that'll hold for any x value greater than or equal to 1. When it's at 1, it's actually the harmonic series. Okay, so you put it all together, and it looks like you have conditional convergence at -1, and then so CC at -1, so you could write it like this, I think. and then absolute convergence from -1 all the way up to 1, not including 1, right? And let's see if that worked the way we put it in. Yeah, okay, so we should be good there. Number 17, it seems like what you're doing is just kind of it's not quite a p-series, right? You know, the series -1 to the n, and I think it was like 1 over n to some p-value. For what p-values does this thing converge? So you're looking at the limit of 1 over n to the p. So as long as p is greater than 0, this is going to be an L over infinity form. And then, you know, you have the ratio test, 1 over n plus 1 to the p all over 1 over n to the p, which will be n to the p, which is something less than n plus 1 to the p when p is greater than 0. So it looks like that, and of course that would be less than 1 for p greater than 0. So the interval where this thing will converge will be 0 to infinity, which is kind of what I wrote there. Yeah. So and I mean, it's kind of a wishy-washy thing, me doing a kind of, you know, an experiment on just particular values. You'd want to prove these things in general to be a bit more careful. But I think this, you know, the p greater than 0 is the best you're going to do for that limit. And you have to have that limit hold for the thing to be convergent because it's an alternating series. Okay, so anyways, that'll about do it for me. Thank you for watching, and I'll see you next time.